Are we alone in the universe? For centuries, that question belonged to philosophers. But today, science is tackling it head-on. We're now reading the geological diaries of other planets, searching for the telltale signs of life etched into the rocks of distant worlds. This is the world of astrogeology, and it might just hold the key to the most profound discovery in human history. Simply put, astrogeology, also known as planetary geology, is the study of the geology of other celestial bodies, planets, moons, asteroids, and comets. It's about understanding how these worlds formed and evolved. Thanks to robotic spacecraft, geologists can now extend their work across the solar system, using orbiters, landers, and rovers as their remote-controlled rock hammers and magnifying glasses. The core of this search revolves around something called a biosignature. A biosignature is any feature, be it a substance, a molecule, or a structure, that serves as evidence for past or present life. The trick is finding a biosignature that couldn't have been formed by non-biological processes. It's a high bar, but scientists have a few key types they look for. First, there are morphological biosignatures, the shapes of life. On Earth, we think of dinosaur bones, but for alien life, which is likely microbial, the targets are more subtle. We're looking for microfossils, the preserved remains of microscopic organisms. A prime example are stromatolites. These are layered rock structures built by microbial mats trapping sediment over time. The oldest accepted evidence for life on our own planet comes from 3.43 billion-year-old stromatolites in Australia. Finding a similar layered, domed structure on Mars would be an electrifying discovery, though scientists would still need to rule out non-biological mineral precipitation, which can sometimes mimic these shapes. Next, we have chemical biosignatures, the molecules of life. Life as we know it is a master chemist, and it leaves behind molecular fossils. Scientists search for lipids, which are fats and waxes that form cell membranes and can survive for billions of years. They also look for amino acids, the building blocks of proteins. Here's a fascinating clue. Life on Earth almost exclusively uses left-handed amino acids. Finding a sample on Mars with a strong preference for one-handedness over the other would be a powerful indicator of biology, because non-biological chemistry tends to produce a 50-50 mix. Another key target is kerogen, a complex organic goo formed from the fossilized remains of things like algae and plankton. Its presence and composition can tell us about what kind of organisms once lived in an environment. Perhaps the most powerful, yet subtle evidence comes from isotopic biosignatures. Isotopes are versions of an element with different masses. Biological processes are a bit lazy. They prefer to work with lighter isotopes because it takes less energy. Take carbon, for example. Life on Earth prefers the lighter carbon-12 over the heavier carbon-13. This means that organic matter, like ancient fossils or kerogen, is measurably lighter in its carbon isotope ratio than the surrounding inorganic rock. This isotopic imbalance is a classic hallmark of life, and it can also be seen in other elements like nitrogen and sulfur. Of course, finding a biosignature is only possible if it survives for billions of years. The key to preservation is rapid burial in fine-grained sediments like mud or clay. This protects the organic remains from being broken down. Mineralization, where minerals like silica replace or encase the organic material, is also crucial. Places like hydrothermal vents are considered prime spots for preservation because minerals precipitate out of the hot water very quickly, potentially entombing entire microbial communities in a geological snapshot. So how do we find these signs on a planet millions of miles away? We use an incredible array of instruments on rovers like Perseverance. It starts with cameras like Mastcam-Z, which acts as the rover's eyes, providing panoramic, zoomable color images to help scientists pick the most interesting rocks to study. Then, for a closer look, the Watson camera on the robotic arm provides hand-lens scale images of rock textures. To figure out what the rocks are made of, we use spectrometers. The SuperCam instrument is a marvel. From over 20 feet away, it fires a laser to vaporize a tiny spot of rock. It analyzes the light from that plasma to determine the rock's elemental composition. SuperCam also uses Raman spectroscopy, which shines a green laser on a target to identify the specific molecules and minerals present, including potential organic compounds. For an even finer scale analysis, the SHERLOC instrument on the robotic arm uses an ultraviolet laser. It's designed to hunt for organics and specific minerals that form in watery environments. Certain organic molecules glow under UV light, and SHERLOC can detect this fluorescence, making it a key tool in the search for life. Paired with SHERLOC is PIXL, which uses a focused X-ray beam to map the elemental composition of a rock down to the size of a grain of salt. And to see what's underground, the RIMFAX instrument uses ground-penetrating radar to map out buried rock layers, revealing ancient river channels or lake beds. But the ultimate analysis can't be done on Mars. That's why Perseverance is carefully collecting and caching rock samples. The plan is for a future mission to pick these samples up and bring them back to Earth, where we can use the full power of our planet's best laboratories to search for definitive proof of life. This hunt has a long, fascinating, and controversial history. It really began in 1976 with the Viking landers on Mars. They carried experiments to look for metabolism in the soil. One experiment, called the labeled release, got a positive hit. It detected a release of gas consistent with microbial life-consuming nutrients. But another instrument, a mass spectrometer, found no organic molecules in the soil. How could you have life without organic building blocks? The consensus became that a weird, non-biological chemical reaction was mimicking life. Decades later, the Phoenix lander discovered perchlorate in the Martian soil, a substance that can destroy organics when heated, which is exactly what the Viking instrument did. The debate over the Viking results continues to this day. Then, in 1996, came the Martian meteorite Allen Hills 84001. Scientists announced they found 4 lines of evidence for fossilized microbial life inside it, including structures that looked like tiny fossilized bacteria and specific magnetic crystals that, on Earth, are made by bacteria. It caused a global sensation, but again, the scientific community pushed back, proposing non-biological explanations for every piece of evidence. The controversy taught us a crucial lesson. The burden of proof is incredibly high. You need multiple, independent lines of evidence that can't be explained away by simple geology or chemistry. This led to the modern strategy on Mars: follow the water. Rovers like Spirit, Opportunity, and Curiosity found overwhelming evidence that Mars was once wet and habitable. Curiosity even found complex organic molecules in the mudstone of an ancient lakebed. Now, Perseverance is taking the next step in Jezero Crater, the site of an ancient river delta. Deltas are fantastic at preserving organic matter. Perseverance is specifically designed to find and characterize biosignatures. It has already examined rocks with organic carbon and minerals that, on Earth, are associated with life. But scientists are cautious, as these can also have non-biological origins. The final verdict will likely have to wait for those samples to be returned to Earth. While Mars gets most of the attention, some of the most exciting targets are now in the outer solar system. Jupiter's moon Europa and Saturn's moon Enceladus are covered in ice, but beneath those shells they're believed to hide vast, global oceans of liquid water. These oceans are kept warm by the constant gravitational squeezing from their giant planets. In fact, the Cassini spacecraft saw geysers of water ice erupting from Enceladus, spewing material from its subsurface ocean directly into space. This gives us a stunning opportunity. A future mission could fly through these plumes and sample an alien ocean without ever needing to land or drill. NASA's Europa Clipper mission, scheduled to launch in 2024, will perform dozens of flybys of Europa to confirm its ocean and scout for future landing sites. The search for life is not easy. The biggest hurdle is what we call the n=1 problem. Our entire understanding of biology is based on one example: life on Earth. Life elsewhere could be completely different, based on a chemistry we can't even imagine. Another major challenge is abiotic mimicry, the fact that non-living chemistry can create features that look tantalizingly like life. This is why any claim of discovery will require an extraordinary amount of evidence. Despite these challenges, we are living in a golden age of astrogeology. With the James Webb Space Telescope peering at distant exoplanets, the Mars Sample Return mission on the horizon, and new missions planned for the ocean worlds, we are closer than ever to answering that fundamental question. The rocks of these distant worlds are ancient libraries, holding stories locked away for billions of years, and right now, we are finally learning how to read their language.